So welcome back. Final example from chapter 9. This example deals with an airline that is concerned that 50% of people who begin an online process to book flights never actually go through with it, never actually pay, and they would like to reduce that percentage. And so to do so, they'd like to reduce the number of pages that people go through from 4 to 2. So they take a random sample of 300 customers and they discover that 117 of them do not actually finish the process. So out of the 300, 117 don't actually go through with paying for the flight. So the question actually asks you to formulate the null and alternative hypothesis in order to test this theory. And the theory that they want tested is the new system, or does the new system reduce the number of non-completion percentage? Does it reduce that value? Right now, the data indicates that 50% of people do not actually go through with it. And the critical value that needs to be used is alpha equal to 10%, 5%, 1%, or a 1/10 of 1%. And so for simplicity's sake, we're just going to use the 5% alpha. Step 1 is always to state the hypothesis. What is our hypothesis? Our hypothesis is HO, HA. We always test the population parameter, and the two choices that we have in terms of population parameters for COM215 is mu or pi being the proportion. If you look through this problem, you see that there's no numbers essentially given, but everything was in terms of percentages. So this is a test for proportion, population proportion. So it's going to be sigma, it's going to be pi, and now we need to know the sign, and we need to know what is our status quo. So the status quo was stated at the beginning of the example. They said that 50% of people do not go through with it. And so we're testing it against 50%. And they have the new system, and they said we would like to know if the new system actually reduces that proportion. And so HA is going to be less than. And if HA is less than, then HO is going to be either equal to, or you can set it as greater than or equal to, whichever is fine. So that is the hypothesis. Step 2. Determine the critical value. So as always, the critical value, you have a choice between Z or T. In order to choose between them, ask yourself, is N large? Is sigma known? Is the distribution normal? In this particular case, we have N is equal to 300, but because this is a proportion, we need to know if N is large in terms of proportions. So N times P is greater than or equal to 5. And N times 1 minus P is greater than or equal to 5. The thing we don't know yet is P, which is easy to calculate. I'm going to go ahead and do it right here. Just going to make this a little smaller. Put that there. So for us, P is going to be 117 divided by 300. In this case, 39. And so 300 times 0.39, is it greater than 5? Yes, it is. 300 times 61%, is it greater than 5? Yes, it is. So therefore, we have a large sample size, so therefore we can use Z. We don't know sigma, that's fine, because we still have a large sample size, and that large sample size also allows us to assume normality with respect to the distribution. So now I know that I need to use Z, and what I'm going to do here is I'm going to erase all of this, and I'm going to keep these and I'm going to put them all in one shot. Just keep them here, nice and tidy. There we go. So we're going to go ahead and use Z. And as I said, just for simplicity's sake, I'm going to use alpha is 5%. Notice that the entire alpha will be in the lower tail because it's a one-tailed test to the left. So if we want to do that, this is your cutoff mark. We need to figure out what this is. And if this is 5%, this has to be 45%. And so if you look this up in the table, Z is going to equal 1.96. Again, we've seen this number before. Or negative 1.96. Make sure that you keep the negative signs in the proper order. Step 3. Calculate the T-stat or test statistic. For us, it's going to be Z star, just to differentiate it from Z, is equal to P bar minus pi divided by the standard error and again, I'm using my own notation, but I'm hopefully explaining it well enough that it should have no issues for you comparing it to the book. So 0.39 minus 0.50 divided by half of 50% times 50% for 300, just like that. And here I find Z star is equal to negative 3.8102. Clearly, it happens here somewhere, negative 3.81. So we are in the rejection zone, so you already should know what the result is. We're rejecting HO. Step 4, conclude. Since the absolute value of negative 3.8102 is greater than the absolute value of negative 1.96, we reject HO. So yes, there is evidence that the new process makes people actually go through with the purchase. There are less people who do not go ahead with the purchase. And finally, step 5, calculate the p-value. Our Z star had a value of negative 3.81. I'm going to keep it as 2 decimal places because the Z table only takes 2 decimal places. So let's go to the Z table. We look up 3.81 in the table. There is no 3.81. The biggest value is 3.59. And therefore, the p-value, as I've explained before, is everything after your test statistic. Well, the biggest test statistic that we have here is has a p-value, has a probability distribution. It goes out almost 50% of the way. So in this particular case, 50% minus 0.4998 is approximately 0. And so the p-value for this guy is also probably approximately equal to 0. Because this value here is 3.59. It's not close, but not too far away from 3.81. So we know that the area underneath the curve after 3.81 should be approximately equal to 0. If this is confusing to anyone, please reach out and let me know how I can explain it differently, or if I should, in the comment section below, please. So since, I'll do this in green, since P is less than alpha, reject HO. 0 is less than 5%, reject HO. You will never get a conclusion here that is different than here. They will both be the same conclusion. So this is an example of hypothesis testing with population proportions, as well as how to solve for a p-value.